So yeah, in this last lecture, the goal is to go through this multi-party protocol, like going through multi-party computation in the quantum setting. And okay, let's start with classical multi-party computation. So the parties, they want to compute jointly this classical function. And as I mentioned before, the security in the security definition, we want that all polynomial type distinguishers not be able to identify if we're running the real world experiment where we have a protocol between the parties, where each party receives some input, and at the end of the protocol, they all output some an arbitrary. So after the protocol, the parties decide to output some arbitrary state. So sorry, here I'm considering that A could also be, for instance, a quantum adversary. Yeah, that interacts with the honest party B. And in the ideal world, we have a simulator that interacts with these adversaries. So there is a simulator will receive this input from the distinguisher, will be able to simulate or run this adversary A tilde, or like forward or backwards. For instance, you can try to do rewinding. And the simulator also interacts with the idea functionality. And the honest party just interacts with the idea functionality. So the idea of showing like that these two cases cannot be distinguished, this will tell us that the input of B is never revealed to the honest adversary in the real case, because when you consider the idea functionality in the middle, we are sure that this ought to happen. Okay, so having an arbitrary, so the bottom line is that having an arbitrary adversary here that would try to learn as much as she can from B will not succeed, because this simulator would be able to retrieve as much as information as A from the idea functionality. So there were questions, I think, about the security definition. Yeah, have I answered them, or do people still have questions? So okay,
there are no new questions that have come up on Slack.
Okay, if they appear, let me know. Okay. And we have that classical multi-party computation is very important. And to demonstrate its importance, okay, we can see that two of the 11 winter schools of Bar-Ilan University were in multi-party computation. So, and I really recommend people to watch these videos. I was watching the videos to prepare my talks, and they're really good. And okay, and it's good. But okay, anyway, like just to highlight that this is an important topic in cryptography. And the classical protocols for multi-party computation, usually they can be split in two families. In the first one is the GMW family, which allows us to do a multi-party protocol, which is secure only against honest or semi-honest adversaries, and enhancing it with the idea functionality of zero knowledge. So for those who know what it is, this is zero knowledge proof of knowledge. And the second family is called the IPS family, which now bootstraps honest multi-party computation, like a multi-party computation against honest adversaries, but it enhances with oblivious transfer. And I'll describe it more details later, what oblivious transfer is. And these protocols, as I said, they work in the classical setting. But URU in 2010 shows that the protocols are also secure against quantum adversaries if we implement these ideal functionalities also against malicious quantum adversaries. But and in order to implement these, like while classically we can implement these ideal functionalities only from public key encryption assumption. So if you remember the words that I said, these functionalities lie in cryptomania. Quantumly, we have problems implementing them because all the classical ways of implementing them require extraction. And classically, extraction is somehow tightly connected with rewinding. But rewind in a different way that we saw for zero knowledge. So it's a harder, we can say that it's a harder type of rewinding that where watches rewinding does not work. So for a long time, it has been open, like how to construct even post-quantum implementations for these functionalities. So but recently we have seen some sort of like 3 types of solution, like how to implement these functionalities and having classical multi-party protocols for against malicious quantum adversaries. And in this first line of solutions, we implemented with an extra trusted setup. So for example, these work by Garg and Srinivasan, they implement a protocol that, for instance, has a common random string available to all the parties. So this CRS should come from a trusted party, and assuming that it was generated correctly, the protocol is secure, even against malicious quantum adversaries. A more recent line of solutions is implementing these functionalities from stronger functionalities or assumptions. For example, in this result by Tansky and Shmueli or Agarwal et al., they use FHE and this kind of like things that are not necessarily in Cryptomania, in order to build to implement these functionalities in a secure way, even against malicious adversaries. And in the third way of solving this problem is instead of using classical protocols to implement these functionalities, is then to add quantum, even like add quantum into the table, putting quantum on the table, even for the honest guys. And it is very interesting because then whenever we put, like in this case specifically, when you put quantum on the table, we can implement these functionalities actually from much weaker assumptions than classically. And yeah, given that I have just 1 hour, I will have to focus on only one of these 3 solutions. And my choice is, not surprising, the third one. So my goal is try to explain how you can have quantum multi-party protocols from weaker assumptions. Is there any question?
No, for now.
Okay. So let's move on. And the first building block is oblivious transfer. And in the ideal functionality of oblivious transfer, we have 2 parties, the sender and the receiver. And the sender sends 2 messages, M0 and M1, to this ideal functionality, whereas the receiver sends just a bit B. And after these 2 messages, the FOT, like the ideal functionality of oblivious transfer, just sends MB to the receiver. So notice that the sender does not learn which B is sent to the receiver, and the receiver is only allowed to learn one of the bits sent by the sender. But of course, we don't live in the ideal world. We need to implement protocols where the sender, which is given, like we need to implement a protocol that we need to propose protocols that implement this ideal functionality. But here, in order, as we need later for build a multi-party computation for oblivious transfer, we need a strong notion of security for these oblivious transfer protocols. And in this security definition, this is the same sort of simulation security that I was discussing for multi-party or 2-party computation. In particular, when you consider, for example, security against malicious receiver, what we want to, like, again, we want to make the real world and the ideal world indistinguishable. So we want that whatever this malicious receiver does when interacting with this honest sender, so an arbitrary quantum malicious quantum receiver that outputs some state rho, should be indistinguishable from this quantum simulator that is able to run this malicious receiver or rewind it. So it has black box, let's say black box access to the receiver. and interacts with the ideal functionality. And the ideal functionality itself interacts with the sender. So this and what we want to show is that the output of this malicious receiver is indistinguishable from the output of this of the simulator. On the other side, on the security against malicious sender, what we want to show is that no matter what the malicious sender does when interacting with this receiver, whatever the sender outputs and the message output by the receiver should be indistinguishable to the ideal case, where in the ideal case, instead of having this malicious sender, we have a simulator that's able to run the sender backwards and forward that interacts with this ideal functionality. And this ideal functionality interacts with the receiver. Okay, and here the simulator outputs her quantum state sigma, and the receiver should output her quantum message MB. So in particular, it's more concrete for the in the case of malicious sender. Notice that the simulator has to, in some way, extract both messages from this malicious sender, which and these messages should be the same messages that the malicious sender would enable the honest receiver to get. Because the point is, if M tilde B is different of MB, these two scenarios are perfectly indistinguishable. So the key point is that their simulator, in some way, like having this leverage of being able to run the malicious sender backwards and forward, should extract both messages. From the malicious sender to be able to input it to the ideal functionality. Okay, and this is the secure definition of OT that you need in order to construct MPC protocols. Any question? Okay, so let me quickly say how to get, or at least the results that allow us to get multi-party computation from quantum plus 1A functions. And the starting point is this protocol by IPS, where they show that MPC protocols can be built from the ideal functionality, so an ideal OT functionality. As I said, Uru then showed that this classical reduction from FOT to MPC, it also holds in the quantum world if you can implement FOT against an arbitrary quantum adversary. And then quantum enters in the room. So Bennett, Brassard, Crépeau, and yeah, I don't remember the last name, sorry. They propose a quantum protocol for OT based on commitment schemes. But these are not the standard commitment schemes that we usually see, like hiding and binding. These are a bit stronger commitment schemes that I'll describe in more details later. But BBCS, they proposed this protocol, but its security proof only appeared almost 20 years later by these two works that show that okay, we can finally prove BBCS protocol, the security of BBCS protocol, if you have these strong classical commitment schemes that I said. And in particular, these strong classical commitment schemes that we need in order to instantiate this BBS protocol, they're likely lie outside the minicrypt. So the point is, if you can build these extractable commitments classically, you can implement, for instance, key agreement. So it's something that we should not believe to be something that lies in minicrypt. And finally, last year, in these two independent works, so the first one by Bartusek et al. And the other one by Grilo et al., we finally show a quantum protocol that allows this strong commitment scheme that we need to instantiate BBCS from one-way functions. Okay, so putting all of these results together, we can finally say that we can have quantum protocols for MPC from one-way function. So in particular, multi-party computation is in mini QCrypt, which is in contrast with the classical case where we don't expect multi-party computation to be mini crypt, given this possibility of black box reduction by Pagliasso and Vodich. And my goal here is to focus on these three bullets here. So talk a bit about this protocol proposed by BBCS and give a sketch of the proof for it, and finally quickly go through how one can build these commitment schemes using quantum protocols. So our focus here is just building OT from quantum and one-way functions. If there's no question, then let me move on. So let me describe the first tentative of BBCS protocol. So as you said, this is a protocol for oblivious transfer. And we have the sender and this receiver. And the protocol, okay, at least this first attempt, it works as follows. The sender will pick random, for some security parameter lambda, we pick random bits x and some random basis theta, and we'll send these states on this basis. So if you remember Roten's talk, this is just a BB84 state. So it's a bunch of pluses or zeros, minus one. So these are random zeros, or like you. Okay, let me say it in a different way. You just pick plus 0, minus, or 1 in format random for each qubit. Okay, this is a different way of saying that. And what we'd like, ideally, in this protocol is that whenever this receiver receives all of these qubits, she decides to some basis that she wants to measure them, and measure each of these qubits, having these outcomes that I call here x hat. Okay, so let's suppose that she's obliged to do these measurements, and then she lost all of these qubits and only keeps this x hat. Then this protocol would say, would tell the sender to send all of these, all of the bases on the clear to the receiver. And notice that whenever this receiver gets this basis theta, she can compare it with the basis that she chose. Okay, and given this comparison, so for example, let's say that the choices of sender is, let's say, plus basis, cross basis, plus basis, cross basis, and the basis chosen by the receiver, let's say it is cross, cross, plus, plus. We have that the receiver, notice that the receiver, who knows both theta and theta hat, can split these bases into sets. The ones where they agree. So, for example, in these two ones, theta and theta hat are the same. And she'll pick the set and call it IB, where B is the bit that she wants to learn. And then she just keeps, she calls the other, and then she calls the other basis that she guessed incorrectly as IB. B, like the complement of B. Okay, and she sends the sets I0 and I1 to the sender. So notice that the sender does not know which set contains the bases that agree and which set contains the bases that don't agree. So the sender just receives both of them, and she has no clue about theta hat. Finally, in the last message of the protocol, the sender can split the choices of the bits X into sets, the one corresponding to Y0 and the one corresponding to Y1. And using these values of XY0 and XY1, she can encrypt the message 0 using key XI0. And here, which encryption you use does not really matter. So let's say, but it should be something information theoretically secure, but I don't want to get into much details here. And she also computes A1, that's the encryption of M1 under the key XY1. And finally, she sends both keys to the receiver. The receiver then, using her XIB, so the X corresponding to the bases that matched, can decrypt AB then to get the message MP. And okay, assuming that both parties are honest, then we have, as I said, the sender cannot distinguish cannot correctly compute the bit B because she cannot distinguish which is the set that contains the right basis and the wrong basis. And on the other hand, the receiver cannot learn two messages because there must be at least one of the bases that was measured incorrectly. And this basis, intuitively, it serves as a one-time pad key in some sense. So whenever you have one bit that was not measured in the correct basis, these will information theoretically hide the message. But the problem with this scheme is that we assume we assume that this measurement, like that receiver measured the qubits as soon as she got them, and this is a very strong assumption because there is a very simple attack where the receiver just waits these bases to come. So she decides not to do the measurement when she receives the qubits, but she waits theta, and just then she performs the measurement. And whenever she delays her measurements, she can all of this she can learn X. She can fully learn X from the sender, and then she can just arbitrarily split the sets IB and IB complement and decrypt both of the messages. Okay, so we need to still to patch this protocol and adding some crypto in order to prevent this attack where the receiver or a malicious receiver waits the basis in order to perform the measurements. Is there any question up to this point?
Seems like people are have like a post-lunch tiredness or something. There's no questions on the Slack.
Okay. Okay, yeah, if at some point, yeah, any question appears, feel free to interrupt me. So as I said, we need to patch this protocol to prevent this attack, and we use it using some crypto. And the crypto that we need is bit commitment. So as we saw before, bit commitment is a two-phase protocol, where in the first one, the committer and the receiver, they interact such that the receiver has a commitment of some message M, And in the second part of the protocol, the committer will open this commitment to the right value M that that was supposed to be. And as I said before, so usually we define binding and hiding properties for a commitment scheme, but here we need a bit stronger notion of security, and this is the sort of simulation security of this bit commitment protocol. And this simulation security of this protocol. So when you're talking about malicious receiver, this property is called equivocality. And intuitively, it says that there is some algorithm that's called equivocator that is able to open the message to a different value, M prime, in such a way that the receiver or the distinguisher won't notice the difference. So whenever this malicious receiver outputs her quantum state, this distinguisher will not see the difference between M and like when the equivocator opened the right message M or some message M prime that's different of M. And of course, this seems counterintuitive because, okay, the point of the commitment scheme is that the committer should only open to a single value M. But notice that the equivocator, it has some extra power than the committer. So for example, this equivocator can rewind this malicious receiver. And this gives this equivocator some leverage in order to be able to change the message being open in the second phase.
There has a question showed up now,
Mm-hmm.
and that's about the plain protocol without bit commitment.
Mm-hmm.
The question is this protocol secure if we assume that storing qubits is not possible?
I think it is. It's called a bounded. I think even if you assume that you have a bounded memory, then I think this protocol is secure. So, as I said, equivocation is somehow the simulation version of hiding. And we also want extractability. That's the simulation version of binding. And the games or the scenarios in this extractability notion is that you have, you have this malicious committer that commits to some message M. And then you have the second phase where it opens. But the point is the extractor, like this algorithm that we call extractor, that's able to run C tilde backwards and forward. It is able to retrieve the message in the first phase already. So by doing, for example, rewinding or using some leveraging that the extractor might have, she'll be able to extract some message M prime. And in order to show that this protocol or this bit commitment scheme is extractable, the idea is that when you put together the output of the malicious committer and the message that she opened in the second phase, this should be indistinguishable from the output of the committer in this in the second case, and the message that the extractor was able to extract in the very first phase. Okay, so in particular, you want M prime to be equals to M. So if there's no questions with these bit commitment schemes, let me go back to BBCS protocol. And let's modify it a little bit. So as I said, the receiver is supposed to get the qubits and measure them right away, but we cannot enforce that. But one thing that we can ask the receiver to do is to commit to the basis and the measurement outcomes that she's supposed to do whenever, like as long as she receives the qubit. Then in order for the sender to be sure that she indeed committed to the right value, so she indeed committed to basis and the measurement, the sender just sends a random subset of lambda, let's say of size, let's say lambda over 2, and the receiver should open the commitments for every I, so for every pair of bases and outcome, when you have for every value that is in T. So the idea is that the receiver will open half of the commitments or half of the measurement outcomes that she was supposed to do. And then the sender can just check, like for every I in T, if theta hat I is equal to theta hat, if theta hat I is equal to theta I, if you have xi equals to xi hat. And if you have any case where this did not happen, then the sender can just abort, because she knows that the receiver did not perform the measurement. Because whenever the point is, whenever the two bases match, the two bits should be exactly the same. If she did so, then if the sender did not detect any suspicious action from the receiver, then they just continue the previous protocol. So the sender then opens all the bases in the clear, and the receiver just splits the base into sets, but now ignoring the set T that was open. So you can just ignore the set T, but then and split the remaining bases likewise. Okay, and then sends I0 and I1 to the sender, which received with the encryption of M0 and M1 to the receiver. So yeah, are there any questions about how to modify this BBCS protocol?
I don't think there are questions about that. There is another question about security of OT, though, or in more general about the security defined by comparison to ideal functionalities. And I think maybe that's good to clarify right now. So the question is, what if, like, the malicious party just refuses to participate, essentially, or sends garbage or whatever? Like, how can you then simulate the ideal functionality?
No, okay, yeah. If you have something like this, then okay. If the, for example, if the receiver here goes away, the simulator, the sender could just abort. Okay, and the same thing that the sender could do the same thing here. Whenever the simulator interacts with the receiver, the idea is that the receiver should not notice that she's interacting with the simulator, and then the simulator will notice that the receiver went away, and the simulator would abort here, and then the probability of abort would be the same in both cases.
Okay, thanks.
So yeah, if there's no other question on BBSS, like on the description of BBS protocol, then I'll give an idea of why it's secure. So I'll show security against a malicious sender and a receiver. Okay, so let's now suppose that you have a malicious sender, and we want to devise a simulator that is able, that is able to extract both bits from the simulator. Because if you remember the security definition, Yeah, the simulator, when you have a malicious sender, the simulator somehow has to extract both messages from the sender without the sender noticing. So I think this is what this scenario is telling. So I'll tell you how the simulator will behave in order to extract these two bits from the sender. And you do this like changing the protocol little by little, and then you'll see why each step would be fine, and why this protocol is secure against a malicious sender. So the first thing that we can change is that instead of the simulator opening the right values, we can use the property that we assume that this commitment scheme is equivocal, and instead of sending the open, just equivocate the opening for an arbitrary value that she wants. So the simulator just chooses which are the values that be open. And again, she's able to do that using some leverage that the simulator has over this malicious sender. And that's why it's not breaking the commitment scheme. Once we are able to equivocate the opening for whichever value that we want, we can just do a dummy commitment here. So commit everything to 0, let's say. And this should not change anything because the equivocation, like from the equivocation, the malicious sender cannot see the difference. And whenever you did these commitments of zeros, since we don't need the measurement outcomes anymore in the second message, we can just delay them, right? So the thing that we need to do is whenever the simulator receives the set T, that's the challenge from this malicious sender, the simulator can just then pick the correct theta for the set T, and this will give you the measurement x for the set T. And notice that this sets theta hat T, they will be uniform, not random. So it's not that she's cheating by measuring the right value. She's just measuring random basis, but on a specific set that will be tested on the specific test that will be performed by the simulator, by the malicious sender. Okay, so let me say it a different way. The first thing that the simulator does is delay the measurement done on the test set after she received the set, she received which set should be tested on. Then, to measure the remaining qubits, the simulator can wait for the values of theta, and then she can actually perform the attack that I mentioned before. Once she has the theta, she can measure all the remaining qubits using these values, using these bases, and therefore retrieving the right value of x. And then she just splits the bases uniformly at random in I0 and I1 and send both of them to the malicious sender. Finally, when she receives the encryption of A0 and A1 by the sender, notice that now the simulator has enough information to decrypt both values at the same time, because since she measured the right basis, she has both keys, and therefore she can decrypt both values. Okay, so this shows, and notice that whenever you did each of these modifications on the protocol, the simulator could not have noticed it. Otherwise, we would break equivocation, we break equivocation of the commitment scheme. So yeah, it seems there are no questions. So let me move to the security against a malicious receiver. So now we have this malicious receiver, and you have a simulator that interact with the receiver, and wants to find out which is the bit B that this malicious receiver is trying to learn. And in order to retrieve this bit, the only thing that the simulator needs to do is to extract the values of the basis theta hat here. So, and we can do this using extractability of the bit commitment scheme. So yeah, so from the commitment you can use the extraction by rewinding our tilde and so on. And once she has the values of theta hat, she can just compute B by distinguishing what are the values, like she can exactly compute which are the bases that match or not. She can decide which is IB, such that theta hat I is equal to theta I. Okay, so extraction, this part of the security proof is much simpler. So it's just about it's all about extracting the commitments. Any question? Okay. So yeah, with this, this was a quick proof of security of BBCS. If you have these commitment schemes that are both equivocal and extractable. But then, as I said, classically, we don't know how to build these using, let's say, one-way function. So we need at least a public encryption. And from public encryption, we have multiparty computation. So why should you use quantum in this case? But then, finally, last year, we have these two independent works that build this extractable and equivocal commitment from quantum and one-way function. And both of these results, they like each of them follows a very different route. And here I won't have much time to talk about each of them, but I can refer to the QAP talk that we had this year. Both of us, we explained a bit more in details how to achieve equivocality and how to achieve extractability from quantum communication, quantum computation. And what is also interesting is that since we use different routes, each of these protocol has different features as well. So, for example, in the works by Bartusz et al., in particular, they have a black box use of one-way functions. So they're from their result, we're showing that this no-go theorem by Impagliazzo and Rudich, it does not really work in the quantum setting. So this is showing this black box separation between classical and quantum one-way functions. On the other hand, in this work by me and my co-authors, our protocol, if you assume some trusted setup, so for example the CRS, then we can actually achieve constant round oblivious transfer, so constant round multi-party computation, and moreover, we have this in the UC security model. So assuming this extra setup, then we can actually have much more efficient and under a stronger, and a protocol much more efficient and under a stronger security notion. Is there any other question so far? Okay, so if not, then I'll switch gears again. And now I'll quickly explain a bit how can, instead of doing quantum protocols for classical multiparty computation, now how we can have protocols for parties that are quantum and want to compute a quantum functionality, meaning that they share some quantum state rho, and they want to compute some unitary on this jointly distributed state row. So just to be even precise, in the ideal world, what we have is that this quantum trusted party, where each party sends their share of this quantum state row. This trusted party applies the unitary on this quantum state and sends back their share of the output of U applied on row. Is there any question? No, okay. As in the classical case, in the ideal world is that, in the real world, we want to implement this protocol. We don't want to live in the ideal world. We want to have a protocol where the parties interact, sending possibly quantum messages, and they're able to compute and share the output of U applied on row without losing their privacy, without having to reveal their inputs on the clear, or without any other party learning anything else from their output. And here, the secure definition is similar to the classical setting. Like the idea is that you want to devise simulators that are able to compute such that there is no distinguisher can see if there is if they're in this ideal world with a simulator or in the real protocol with its adversaries. So yeah, compared to classical multiparty computation, its quantum version, like multiparty quantum computation, is much more recent. But still, it's fairly rich. So we have protocols with different flavors. So for example, we also have multiparty quantum computation protocols that are statistically secure if you have an honest majority. And these protocols also rely on error correcting codes, computing on encoded data, and as in the classical setting. We have more recent protocols which is not like for arbitrary multi-party computation, but for the specific case where I have two parties and one of them is dishonest. Finally, we have then we have multi-party quantum computation, where we allow we allow multiple parties to be dishonest, like meaning you have k parties, and there are some subsets of malicious parties that are tolerated. So for example, there is some subsets of these parties for which, if you have this set Si in this allowed subset, then the protocol will be secure. But if you have a set some set of adversaries that's not in this allowed set, then the protocol could completely fail, like the security proof completely fail. And finally, the last case is having a multi-party quantum computation protocol, which is computationally secure, but now we have an arbitrary dishonest majority. Okay, and this is closer to these classical protocols that I was saying, where we could have up to k-1 dishonest parties, and still we can prove that the protocol is secure. And I'll focus on this the last line of protocols. And okay, the last protocol, actually, this was proposed by Dulek et al. And the result, it is an extension of the two-party case to the multi-party setting. And in particular, they built multi-party quantum computation protocols, assuming an ideal and classical multi-party computation functionality. Okay, so and for now on, I assume that this trusted party exists, and she can, and from that, I'll tell you how to build multi-party quantum computation protocols. And the main building block of our protocol is using Clifford encoding. And just to recall Henry's and Thomas' lectures, The Clifford's operations are the unit that is generated by Hadamard P gate and C naught gates. And I'll denote by CM as all the possible Clifford circuits on M qubits. I don't want. Okay, yeah, I don't want to get to details what Clifford are or like. I'll just focus now on why choosing Clifford operations would be good for us. And the way that you're using Clifford operations is to encode an n-qubit state psi under using some security parameter lambda. And this will be done by picking a random lambda plus n qubit Clifford C and apply this random Clifford on psi appended to lambda ancilla 0 qubits. Okay, so it will be applying this random Clifford on psi tensor 0 lambda. And why do we like Clifford encoding? So first, we have privacy. So as we saw before, when you apply random Paulis, you have a quantum one-time pad. And Clifford operations, they subsume Pauli operations. So in particular, picking a random Clifford, we have that C psi is one-time padded for every state psi. But more importantly, we don't only have privacy, but we also have authentication. Meaning that no matter what an adversary does, whatever whatever she does on an encoded, like in this Clifford encoding of some state psi, whenever we undo the encoding, so whenever we apply the inverse of this of this Clifford, we have that the traps are 0 if and only if this like with high probability, if and only if this malicious operation is trivial, meaning that they didn't do anything. Okay, so yeah, if you don't have this adversary, of course you're going back to psi 0 lambda, 0 lambda. And what the authentication of Clifford secret says that if you have something different of identity here, then you catch the adversary with probability 1 minus negligible. Okay, let us see how we use this. So, and let us focus now only on a single pure qubit, and these will contain already all main ideas that we need for our protocol. And the first idea is that, okay, when you have a single qubit psi and we want it to be in the protocol, is that one of the parties will hold the Clifford encoding of this state psi, of this qubit psi, but nobody knows C alone. So the idea is that this Clifford C will be shared among all of the parties in a secret way. So in particular, we can decompose C with random Clifford C1 up to CK, such that C is equal to CK multiplied CK times CK minus 1 up to C1. So in particular, this says that if you have an honest party that don't share their CI, then C is completely unknown. Okay. And okay, our second key point to perform protocols for multi-party quantum computation is this public authentication test, where you notice that here our instead of having lambda trap qubits, we use 2 lambda, and the idea is that half of these trap qubits will be used to test authentication, like in a public way. And the remaining lambda ancilla qubits will be used to keep privacy authentication even during this test. So the point is we don't want that in this test that you lose the state. We need that during the test, like even during the test, the authentication and privacy of the qubits will be maintained. Are there any questions? So let me go quickly through the protocol. Oh, and then on that, okay, with that we do computation on encoded data. So let me explain roughly how we do the encoding. And the idea is that the MPC will send these random Cliffords to each of the parties. So they pick CI at random and send to PI. And these parties just send this state, the parties will send this state around the table and apply the corresponding random Clifford that they received from the MPC. So for example, P1 will send the state C1 applied to phi and appended ancillaries to P2, and so on, up to pk minus 1 that applies ck minus 1 to the state that she received and send it to pk, who will then send the state back to P1, applying her unit operation ck. But the question is, how can, so the point is, because of no cloning, we need to pass this quantum state sequentially to everyone and then have it back to P1. But then the question is, how can we be sure that nobody tampered with the state, or nobody replaced it with a different one, or did something that they should not have done? And there it comes, like for that we have our public authentication test. And let me describe it quickly. So the idea is that, let's say that P1, she has some quantum state psi, which is supposed to be the correct encoding of some state phi that she chose. But she does not know if each party, for example, behaved honestly. So in order to enable this public authentication test, this ideal MPC functionality, we compute a random Clifford C prime on all of the qubits. Compute a random Clifford C prime and E, a random linear function U, and a random value R, in such a way that C prime is equal to undoing the previous Clifford encoding. So this is the undoing the previous Clifford encoding. This linear function will happen on the 2 lambda ancilla qubits. And finally, this R is one-time padding the last lambda ancilla qubits. Okay, so and this the MPC computes these values and send it to P1, who then is supposed to apply C prime on this state psi that's supposed to be the encoded state. In the honest case, if nobody tampered with the state, we can check that C prime applied to this state will just undo the encoding, apply a random linear function to zeros, but then the resulting thing is zeros. Finally, applying a one-time pad on the last lambda qubits and some random Clifford on the first, on the data qubit and the first lambda qubits. So that's the honest case, but in the dishonest case, by the properties of this Clifford encoding, we have that the last lambda qubits, they are different of this one-time pad R with overwhelming probability. And in particular, the value of this R last bits, they are unknown to all parties, because since they don't fully know all of the CIs, it means that this random linear function will scramble everything, and on top of that, one-time pad it. Finally, in order to make this test indeed public, we have the parties to interact with this ideal functionality for multi-party computation to check if the value that you have in the traps are correct. So indeed, that this value that you have here, it's R and not something different. okay, and then you have to work a bit further in order to re-randomize the encoding of the state in the honest case and so on. But yeah, I want to ignore these details for now. And the final key point is how can you apply gates on these encoded states? And we can split this gate application in 3 steps. So in the first one, we just consider 1-qubit Cliffords. And this can be done in some sense classically by just changing the key, the key of the Clifford encoding. Because you can think that, okay, instead of having the Clifford key C1 up to CK, we just change the first key to be C1 prime in such a way that C1 prime is equal to C1 D diagram. And then you can see that when you decoded it, when you decode this, then you apply an extra D onto the value. In order to do a CNOT, you need to, so the problem here that why you could do 1-qubit Clifford but not a CNOT is that every qubit is encoded independently. And in order to remedy this, in the CNOT subprotocol, we just need to send both qubits to a single party who re-randomize the encoding and encode them together, apply the CNOT, and decode everything. Finally, in order to apply a T-gate, because, okay, as we saw in Henry's talk, Clifford operations are not universal for quantum or classical computation. So in order to do universal computation, you need to go to outside Clifford. So in particular, we have these T-gates. And we do, the point is we don't know how to apply the T-gates on the Clifford encoding, but if you're given these auxiliary states that we call magic T states, then we can use this magic, like this T gadget that you have here, in order to compute the encoding of T on the state psi. And notice that all of the operations in this gadget, like the CNOT, the measurement, and the Pauli, they can be done with only Clifford operations. Of course, the question here is how can you create these T magic states? And for that, we have a protocol. But I think I'm out of time, so I don't want to get to details. But the idea is that you have one party to create the T states and the other one to test if these T magic states are indeed correct. And just to wrap up, so with all of these parties, all of these parts of these sub-protocols, we can then define this protocol for multi-party quantum computation, where first the parties create these auxiliary T states, then they encode each one of them their input qubits, they apply each gate one by one using their sub-protocols, and finally they decode their own output using, like, with the help of the ideal functionality. So yeah, just to summarize, what I tried with my talk is, or my lectures, is to give a glimpse of what's happening in zero knowledge and multi-party computation in the quantum world. And I think given 3 hours, it's hard to talk about all of these and be complete in the literature. But I try to highlight some of the main or some of the basic results on this area. But still, we're far, like, even classically, we're far from being done studying this protocol, or like studying the subjects, let alone quantum. So there are plenty of open questions involving quantum zero knowledge and quantum multi-party computation. And with that, I'd like to finish. So thank you for your attention.
Thank you very much, Alex, for a great session. I'm sure it will be a good starting point for anyone who wants to understand or start doing research in this area. So with that, we conclude this session, and please join us for the evening session.
So
Don't
yeah, I
worry.
can. Okay, I can still answer questions if there are any.
Yeah, sure.
Okay.
Yeah, so there's one question left that we kind of delayed to asking in the end because it came after you finished that part of your lecture, and that is about the security of commitment schemes. The question is, what is special about UC security? So why does the simulation-based security that you described not already imply UC security?
Okay, yeah, this is very subtle. So the point with UC security is that the protocol should be secure. Okay, let me say it in a different way. So UC security means that even whenever the distinguisher, or sometimes it's called environment, talks to the parties in between the rounds. So it's not that the environment just gives the input and receives the output. It can interact with the parties during all the time. And in particular, in order to prove UC security, usually, or you cannot do rewinding, because this rewinding somehow allows the distinguisher to know if they are running the ideal protocol or the real one. Because in real world, we do not have rewinding. And in UC security, the distinguisher, if you rewind, the distinguisher will be able to detect rewinding somehow. So in particular, so the definition of UC security is much more complicated, at least for me. But as a rule of thumb, for example, is that if you have rewinding, it won't be UC secure.